Okay, welcome back. This is 14.8 on Jacobians. And basically, this is just doing substitutions in 3 dimensions or higher dimensions. And so recall U subs. Um, and, and basically, we have 2 types of U subs. So let's look at this guy, sine of x squared dx. This x squared is inside the sine. The first way you're taught to do a U sub would be if you could identify a function and its derivative inside the integral, then let the U be equal to that function. Okay, so you'll have U equaling some function of x, right? And then you would get the differential du, which would be 2x dx. And that's the part that's going to be causing us trouble, is this replacement of this expression here. So to do it with a U sub, you would solve for dx, and when you would get du over 2x. Okay. Then you would do your sub, right? So you would have x times sine of u times dx, which is now du over 2x. And then you could factor out a 1/2, and the x's would cancel, and everything would be fine and dandy. Okay. So you could plot the 1/2, an integral of sine of u du. Okay. So that's one type of U sub. The actual sub that we're doing now is more like the trigonometric subs that you had. So this would be one type of U sub. The other type of sub is more like the trig subs. So in particular, you could attack the same problem in this manner. Okay. It's just you have to be a little more clever about the way you pick your substitution than you were over here. So you kind of, instead of letting u equal something, you're going to do a substitution for x. And in particular, from our knowledge over here, from having done these kind of problems, we know it's probably square root u. Okay? So I'm replacing x with square root u everywhere. So I'll have the integral of square root u times sine of u times dx, which is now going to be the differential of this thing. So dx will be 1 all over 2 square root u du. Okay. So the derivative of the square root of u, just think of it as u to the 1/2, bring down the 1/2, it'll be u to the negative 1/2, and then drop the u to the negative 1/2 in the denominator. Okay. Okay, so this is basically your second kind of U sub. And you have the same result. It's just that this sub is more along the lines of the Jacobian, the way we're going to do it in this section. Okay, and in particular, this factor here is going to be basically our Jacobian. Okay, so this is what we'll call the Jacobian. Okay, so the problem is the way it's presented in the book. You're probably more used to doing U subs than you are doing these kind of subs. So you're always trying to think in terms of a U sub, and it kind of seems like they're doing stuff in reverse. And it is basically because they're really doing this kind of substitution, not this kind of substitution. You can do the Jacobians like a U sub though, okay? And I was going online, researching the what is a Jacobian, how do I interpret it? And I encourage all of you to do the same. Don't take my word for it. But Mark Eichenlaub is an educational researcher, and where is he? I don't know. He's in Massachusetts or some place like that. Um, but I was going around and I saw in Quora, which is kind of like one of those question places, people post questions. Um, he notes in Quora the sort of how to do a Jacobian with a U sub. Okay, so the opposite direction of what you will read in the book, or hopefully you've already read it, but um, the way they're doing it in the book is kind of a geometric exploration. You know, geometrically, why is it that we can replace this dx with this du thingamajig? What is the relationship between the dx and the du? Okay, and that's what he looks at in this Quora notes. So I went on Desmos. I took an example similar to what he uses, and just went on Desmos and tried to attempt to explain the way he explains it right here. So if you look at the function y equals x sine of x squared, what is this thing? Well, if you graph it from 1 to 5, it'll kind of look like this. It'll go up, and then it'll start oscillating really dramatically on and on forever. Okay. On the other hand, if you look at y equals after the u sub, square root of u sine u, it'll be stretched out. Okay, so you'll end up with this kind of looking expression instead. Okay. So what Mark Eichenlaub is kind of saying, and I don't, I'm not 100% on this, but the way it seems to me is you're kind of comparing the dx or the delta x over here and the rectangle over top of it to the du over here. Okay, and if you do this kind of substitution, what's going to happen is and I made it a little too small. What's going to happen is your rectangle, and of course I ran out of ink with that pen. Your rectangle is going to get stretched out. Okay, so he says that in doing the U sub, it changes the geometry of your Riemann sum, kind of. And you need to kind of compare this thing, okay, this a sub, we'll call it a sub 1, to this guy right here, which we can call a sub 2, right? And a sub 1, in this case, will equal a sub 2 divided by 2 square root u, which is that Jacobian factor back here. And you can kind of see that this thing is getting stretched out. It's bigger. So in order to make, how does this relate to this? Well, this thing is a fraction of this thing. Okay? And if you want to, go read his exploration. I think it's really interesting. I'm not 100% sold on it. And I think there's reasons why the book is doing the method they're doing as opposed to what Mark did. But if you're confused, you can go and look at his work. And I think he has some really cool animations and stuff to go along with it. Okay, so you'll feel better about the Jacobian. You may not still understand it, but you'll feel better about it. Okay. Okay, so what we want to do is basically this kind of U sub process, but it's not really the U sub, it's more like a trig sub. And in particular, this differential is a troublemaker. Now, this dx for us is really going to be a delta x, or if you rather dx dy, delta y. And because we're in multivariables, taking a differential like this, doing a differential isn't exactly the same as doing a differential in 2 dimensions, right? Because in 3 dimensions now you have kind of a slope in the x direction and a slope in the y direction that determine the overall slope. And on top of that, here you have a product of these things. Okay, so it's not entirely clear how I would form this object. And the Jacobian is going to tell you how to form that object. Okay, so right, so let's move on to that. So the change of variables for the double integrals is what we're kind of after. Change variables for double integral. Maybe before we get there, there's one clever thing about doing these two different kinds of subs. I just want to recall trig subs really quick. I hate to take a side path, but you can always fast forward in the video. Recall the trig sub. So you may have something like the 1 minus x squared to the 3/2, right? Dx. And depending on the expression here, that would tell you what kind of u sub to do. So generally you would have to say, let x, in this case, equal sine theta. And then you would say, okay, dx must equal cosine theta d theta. And then you could do your substitutions. And then this would be the integral of 1 minus sine squared theta to the 3/2, and then times dx, which is cosine theta d theta. And then you would have to go, all right, this part here is cosine squared theta to the 3/2 times cosine theta d theta. And then this thing would be cosine cubed times cosine theta, which would be cosine to the 4th theta d theta, and so on and so forth, right? What I'm saying is you could always do a trig sub via a u sub, but you have to be kind of cognizant of the derivatives of the inverse trig functions, right? So with a u sub, how would this work? You could, based off what you see in your integral, you kind of have to compare and contrast that to the derivative of the inverse functions. So in my brain, I'm thinking, all right, the derivative with respect to x of sine inverse x is 1 all over the square root of 1 minus x squared. The other subs possible, leaving differential pieces. Tangent, we want tangent. Okay, so tangent inverse x is 1 over 1 plus x squared. And then the derivative with respect to x of secant inverse x is 1 all over x square root of x squared minus 1. Okay, so there's 3 basic forms here. There's this one, and this one. And if you see one of those forms in your integral, that's going to be the u sub. Okay, so in particular, if you see the 1 minus x squared, that will be similar to this derivative, and so you'll do a u sub for u equals sine inverse x. Okay, okay, so let's try it, right? Let's say, all right, let's see if you're right. Let's let u equal sine inverse x, and then you get du with respect to x, or let's just get the differential, right? Du is going to be 1 all over the square root of 1 minus x squared dx, and then dx will equal the square root of 1 minus x squared du. Okay. So I can rewrite this thing as the integral of 1 minus x squared to the 3/2 times dx, which is now 1 minus x squared to the 1/2, and then du, right? And then I can clean all this up. So this will equal the integral of 1 minus x squared to the 4/2, which is just 2, du. And I need to get everything in terms of u, right? So what you end up having to do is like, okay, I can work with this given information, in particular this, and say x must be equal to sine of u, right? And then replace x with sine u, and you get this, the integral of 1 minus sine squared u squared du, and 1 minus sine squared u, of course, is cosine squared u. So you end up with cosine squared squared, which is cosine to the 4th u du, which of course is, and there's the punchline, right? The same thing that we got doing trigonometric substitution. Okay, so my point being is you could do these subs in either way you want, and it's mainly dependent on us for humans, our ability to remember things and to kind of match patterns. Okay, and with that in mind, you can do these Jacobians in both directions. Okay, they don't note that in the book, but you can. So if you're a little confused as to the way they've chosen to do things, which seems a bit backwards with regards to the geometry, like in Mark Eichenlob's exploration, he does it in the this forward kind of way, but the book is going to do it in a backwards kind of way. All right? Okay. You can do it either way, is my point. Okay. So anyways, getting back then to the change in variables. Basically, you're going to have some double integral in terms of maybe x and y, and then you'll have some area element increment. So usually we'll put dx, dy, right? But we can also write dA. Okay, so this is just your dx, dy thing. Okay, we want to do a substitution for x and y. So instead of letting x equal some function of theta for a trig sub, here we're letting x equals some function of u and v. So we'll have something like g of u and v, and then h of u and v. Okay, so it's a lot more complicated with all the variables. And then we're going to have to change this dA element. Okay, so just like in the u sub, we changed dA to maybe something like du over 2 squared u. We have to do the same thing here. And the way we're going to do it is with the Jacobian, which will basically just kind of be a formula for finding the area of a parallelogram. Okay, so because all of these things represent areas, right? And remember our exploration with the Riemann man, what this thing is kind of an integral over some region in the xy plane. Okay. Sorry if I didn't exactly put it in the xy plane, but it's the integral over one of these regions, and this area element represents one of these rectangles in the xy plane. Okay, so maybe my axis should be more like that. So we want to rewrite that area of that rectangle in this new variable system. In order to do that, we can use this determinant, which is a measure of the area of the parallelogram drawn out by vectors. Okay, so I don't know, we'll get there. So anyways, we can symbolize this in the book with the partial with respect to xy over the partial respect to uv times du dv, or dv du, whichever one you want. Okay, and that's going to be the way we do our subs. Okay, so we need a formula for this object, and this object is the magnitude of this determinant. Okay, and what is this thing? Well, in this direction, and you could go in the other direction as well, this thing turns out to be the magnitude of the partial of x with respect to u times the partial of y with respect to v minus the partial of x with respect to v times the partial of y with respect to u. Okay. Hopefully I didn't get those reversed. Okay. So here comes the geometry now, and it seems backwards, but like again, like I was saying, you could do it in the other direction as well. So what the book is going to do is kind of start in the UV plane and consider a little rectangle there that we're integrating over. Okay, so you can imagine a rectangle like this, but now we're in the UV plane instead of the XY plane. Okay, we want to consider a real small rectangle, because the idea is if the transformation is not crazy, then a real small rectangle here will be basically a real small kind of rectangle over here, maybe some warped type rectangle for a parallelogram of some sort. Okay, and then over here is the XY plane. So we want to see what happens as we go from here to here, and in doing so, we'll be able to obtain a formula for the area element, dx dy, which is our dA, in terms of u's and v's. Okay. Okay. They call that locally linear. And if you remember, back when we were doing like Maclaurin polynomials and stuff like that, you could think of or even just in Calc 1 where you're doing tangent line approximations. When you get really close to the place where the tangent line is hitting the curve, the tangent line and the curve are almost exactly the same. And that's kind of what, I think that's kind of what they're getting at with this idea of locally linear. A box over here is basically going to, if it's really small, is basically going to be a box over here. Okay? So when we talk about our box, we'll put this point at UV, and then we're just going to consider real small changes. Okay, so we go from U to U plus some little change in U, and then on the V-axis, we'll go from V to some real small change in V. Okay, and then our points, we need to see what happens as we do this substitution here with G of UV and H of UV, right? So we have that going on. X will end up being G of U comma V, and Y will end up being H of U comma V. Okay. The book is calling that transformation T of U comma V. Okay, which equals the XY. Okay, so what are these points over here? Well, I get this point is going to be U comma V plus change in V. This point, or let's do this point first, right, is U plus change in U comma V. And then this point right here is going to be U plus change in U comma V plus change in V. Okay. Okay, so I want to see what happens to these points under this transformation. And in particular, I need to compare the area here, which we could call A1, but I think the book calls it S. I'll just call it A sub 1. I want to compare that area to this area over here, A sub 2. Okay. And basically, how do I find the area of a parallelogram? Well, we're leading into vector calculus, so we're going to do this with vectors. You can use other formulas to get the parallelogram. You'll probably get the same sort of spiel. But what we want to do is kind of figure out the vectors from this point to this point and this point to this point. Okay? So this point here is going to be T of this point here. So we'll call this one M. Let's call this Q, and let's call this N. Okay, so I need the vector for MQ and MN. So first off, let's just note what the heck M and these guys are as points. M is going to be the point that's the result of transforming this UV using these functions. Okay, so M is going to be G of UV comma H of UV. And then Q is going to be the transformation of this thing. So it's going to end up being G of U comma V plus change in V, comma H of U comma V plus change in V. And over here, we're after this. We want to figure out what this is in terms of u's and v's. Okay. Uh, so what else? I need n, right, for my vectors. So n is going to be g of u plus change in v, comma v, and then it's u plus change in u, comma v. My u's and v's almost look exactly the same. I apologize. And then comma h, right? So h of u plus change in u, comma v. Okay. And then I need to figure out these vectors. So why I'm after the vectors is because the area of this parallelogram A2 will be equal to the magnitude of the cross product of MQ and MN. Okay, and this fact is from way back in 11 point something. Okay, when we first introduced the cross products, we had a ton of little factoids about cross products, just like we had a ton of little factoids about dot products. Dot products and cross products are like pseudo products, and that they're not exactly going to give you the same algebraic properties as the product and the real numbers, multiplication, right? There's issues like commutativity that don't hold for cross products. So we call it a pseudo product. Anyways, in that section, there's a whole thing on properties of cross products, and this is one of the properties. Okay, it's kind of like the dot product is equal to the magnitudes of the vectors times cosine theta. That was one of the dot product properties. We had all these cross product properties too, and this is one of them. Okay. There's other ways to get that area, but this is the way the book uses, and we want to get you prepared for vector calculus, so we go with this. Okay, so anyways, I need to then get these vectors so I can do this cross product thing. Okay. And this is kind of clever as well. So let's look at what MQ is, and there's going to be a little bit of simplification we could do. So if you remember, how do I create a vector from points in the plane? You take differences, right? So MQ is going to be this minus this, comma, this minus this. Okay, so it's G of U, comma, V plus change in V, minus G of U, comma, V, comma, H of U, comma, V plus change in V, minus H of U, comma, V, and then that's it. Okay, so why is this cool? Look at this guy. The numerator is the frickin' difference quotient for the partial derivative of G with respect to V. Okay, so remember difference quotients, right? Difference quotients. We started out in Calc 1, noting f prime of x was equal to f of x plus change in x minus f of x all over change in x. Now in Calc 2, we have f with respect to x of x comma y is equal to f of x plus change in x comma y minus f of x comma y all over, change in x all over change in x, right? And it's the limit of these things. Okay. So this numerator here is basically just this thing right here, which leads us to the idea that we can approximate this thing then just by saying, okay, this is the partial derivative of G, and G is really just this x function that we've created here. Okay, so the partial derivative of G is just the partial derivative of x. And in particular, this is the partial derivative of g with respect to v. Okay, so I can kind of replace it, but I have to watch, there's no change in v right here. So if I had the change in v, that would be awesome, because then it would be obvious, but I don't. I don't have that. So what I need to do over here is multiply by that. Okay, so over here, it's going to be the partial derivative of x with respect to u, but then times change in v. Okay? And then likewise, this will be the partial derivative of y with, and this should have been v, sorry, partial derivative of x with respect to v times change in v. And then this will be the partial derivative of y with respect to v times change in v. Okay. Okay, for similar reasons then, the other vector mn will just be the partial derivative of x with respect to u times change in u, comma, the partial derivative of y with respect to u times change in u. Okay. So if you put that together and then do this, you're going to get this weird cross product, right? With these this times this minus this times this, right? And what do you got? You basically have xv yu minus yv xu. And if you look back here, that's kind of what we need, right? xv yu minus, and its absolute value, so it doesn't really matter what order we got it in, xu yv. Right? So as long as they're kind of x with u, y with v, and then x with v, y with u, we got it. We nailed it. So I'll dispense with those details and just note then that this area, dA, so now we can finally make our final statement. dA, which is dx dy, is equal to the magnitude of that cross product. And I'll try this, smush it in here. So I'm going xu du, comma yu dy du crossed with xv delta v, comma yv delta v. And this thing, if you go through the messy details, will end up being what we think we need, right? It's xu, so the partial of, let me write it in the normal kind of way, in more Leibniz notation, partial u with respect to, sorry, the partial of x with respect to u, times the partial of y with respect to v, minus the partial of y with respect to u, times the partial of x with respect to v, times dv du. Okay. And that does it. That's the replacement. That's the way we're going to pull off our substitutions. Okay. Okay. So that's about it. Let's look at what the book has for us, right? Okay, so crud, I lost a page of my notes somewhere. That's okay. I don't know what number it is. We'll just call it an example. Okay. So they give us a region in the xy plane, which is not nice. If you were to have to do this via, I don't know, okay, so it's just, a simple example for us to apply the Jacobian to. Okay, so what we want to do is take this region and turn it into a square. And because we do this because it's easier to integrate over a square than this diamond thing, right? So I'm hoping to to go into the UV plane and take this area region and kind of rotate it. Okay? Okay, so how do I do that? Well, I need to get some substitutions for x and y in terms of u's and v's. Right? So first I'm going to just note what these lines are. And these positions are 1, 1, -1, and -1. Okay? Okay, so I get equations for these lines. This equation here is y equals, the slope is down 1 over 1, so -x, and then the y-intercept is 1, so +1. And then this line has the same slope, right? So y equals -x. Its intercept is -1, so I have -1. Okay? And then I get equations for these two lines. Right? So I'll have y equals this time positive x plus 1 for this line. And then y equals positive x minus 1 for its this line here. I want to do a u sub that will cause like a box, basically. And it's not entirely clear, but the way we do it is kind of, I'm going to say my u is based off of these things. So I'm going to let note that y plus x is equal to 1 and y plus x is equal to -1. Okay, and then I'm going to say, all right, because of this, I'm going to let u equal y plus x. Over here, what do I have? Well, I have y minus x is equal to 1, and then y minus x is equal to -1. So I'm going to let v equal y minus x. And then from these two equations, I can determine my y and x formulas to convert into u's and v's. Okay. But in the meantime, we can kind of look at the geometry of what's been created here. In particular, what's happening is I'm going from u equals -1 to u equals +1. Okay, so u is kind of being varying from -1 to 1, right? So you could draw that up here on the UV plane. So u equals -1 could just be a vertical line here. U equals +1 is a vertical line here. And then likewise with this guy, it seems that v is going from -1 to 1 as well. Okay, so v equals 1 here to v equals 1 here, and we got a box. Okay, we've essentially rotated this thing to make it look like a box. So the bounds on our integral will be a lot easier, right? So curve the curve and then point to point. All right, so next I need to get equations for x and y in terms of u's and v's. Okay. So I can use these formulas to pull that off. So I need these formulas from before. I need some formula x equals g of u comma v, and y equals h of u comma v, right? And from that, I can get my Jacobian. Okay. I should have noted the integral we want to integrate back here over. So we're integrating this thing over this region R, and let's call this S. So I'm integrating over the region R, okay, 4 times x squared plus y squared dA, which would be a nightmare if you use these as your bounds on your integral in here. I presume it would. I hadn't tried it. I'm not going to. You can try it. Okay. All right. So going from here to here. Anyways, I need these two functions, and I have that u is equal to y plus v, and then v is equal to y minus x, or y plus x, and then v. Okay, so from here, you can get the formulas g and h, right? So I'll solve this guy for y. So y is equal to u minus x, and then I could back sub this guy into here. So v equals u minus x. So v equals u minus 2x. I'm trying to get a formula for x in terms of u's and v's. So 2x is equal to u minus v, and then x is equal to u minus v all over 2. Okay? And then similarly, then I can get the formula for y by subbing back into here. Okay? So y will equal u minus u minus v all over 2. Okay? So y equals u over 2, 2u over 2, sorry, minus u minus v over 2. And if you combine the common denominators, you get that. In other words, y is equal to 2, just 1u minus v all over 2. Okay. So I got my x and y functions. Right. Now I want to get the Jacobian. Right? And so hopefully I'm not screwing up the symbols. I believe it was this in general. But what was it? It's the absolute value of the partial of x with respect to v times the partial of y with respect to u minus the partial of x with respect to u times the partial of y with respect to v. Okay. So the partial of x with respect to v will just be u over 2 minus v over 2. U over 2 will be 0, minus v over 2 will be minus 1/2. And then the partial of y with respect to u will be u over 2 minus v over 2 is y. So the partial of y with respect to u will be 1/2 minus 0. So 1/2 minus now the partial of this with respect to, did I already do u? Seems like, oh, with respect to u, so it would be positive 1/2. And then the partial of this with respect to v will be negative. So I screwed up somewhere. Partial of x with respect to v is negative 1/2. Then the partial of y with respect to u is positive 1/2 minus the partial of x with respect to u, which is positive 1/2, times the partial of y with respect to v, which is minus 1/2. Crap, I fricked something up. Oh, I forgot to distribute right here. Oh, blast. So this would be u plus v, sorry. Sorry about that. That's what I get for skipping steps. So anyways, then the partial of x with respect to v will be negative 1/2. The partial of y with respect to u will be positive 1/2. The partial of x with respect to u will be positive 1/2. The partial of y with respect to v will also be positive 1/2. So you end up with negative 1/4 minus 1/4 is minus 2/4. The absolute value of that is 2/4, and then that's equal to 1/2, which is our Jacobian. Okay, almost there. So now we need to do our substitutions in our integral. So originally it's 4x squared plus y squared dA. Now we have 4 times x squared, which is this thing squared, which seems like a nightmare, but you can do it. It's just some foiling up top, u minus v squared over 4. So we have a 4 down here. U minus v squared is u squared minus 2uv plus v squared. And then plus y squared, which is u squared plus 2uv plus v squared all over 4. And then times dA, which is now the Jacobian times du dv. So it'd be 1/2 times du dv. Because we're going over rectangle, we know the limits on our integrals are going to both be negative 1 to 1. just the sides of the boxes. If you don't like that, you can do the Riemann man and go curve to curve, point to point. Okay, now we need to clean this junk up. And it looks painful, it's not though, okay? So I have the double integral, the 4's will cancel out, and then I have a 1/2 I could pull out front. Combining the numerators here, you'll get 2u squared plus 2v squared. Okay. And then it's just turning the cranks, right? So you get 1/2 double integral. Whoops, let's go ahead and integrate one level. So 1/2 integral 2u cubed over 3 plus 2v cubed all over 3, and then times du dv, and now it's just times dv, and I have to evaluate from -1 to 1. Okay. When I plug in 1, I'll get, okay, so let's go ahead and do it. I don't want to skip steps and screw up. I plug in 1, I'll get 2/3. I plug in 1 for u, plus 2v cubed over 3 minus, plug in 1 for just plug in -1 now. So -1 for u cubed is -2 all over 3. And then, yeah, sorry, I'm having a brain issue. What did I screw up? Oh, I see what I screwed up. Sorry, this isn't right. Ugh. Almost at the end. Okay. So when I integrate with respect to u there, let's see, this guy will be certainly 2u cubed all over 3, but this guy is not, right? This guy is plus 2v squared u. Sorry, that was the problem. Okay. Okay, and then we can now evaluate, and everything should be okay. So you're plugging in 1 here, then you get 2/3 plus 2v squared, plugging in 1 for u, and I'm plugging -1 in for u. I get now -2/3, and then -1 for u here, minus 2v squared, and we're at dv. So this will be 1/2 integral of 2/3 plus 2/3 is 4/3. And then 2v squared plus 2v squared is plus 4v squared dv. And then I integrate these guys with respect to v, and I end up with 1/2 times 4/3 v plus 4v cubed over 3. And evaluate that from -1 to 1. Okay, plugging in 1, I get 1/2 times 4/3 plus 4/3, and then plugging in -1 minus -4/3 minus 4/3, and then there's 1, 2, 3, 4 4/3, which is 16/3 times 1/2 is 8/3. Okay, sorry about the mistakes on the last one. I was getting, I'm just, I really, okay. Thanks for watching. See you next time.